Welcome to Chapter 2. I'm Jim Burnham. We're talking today about states of matter. Imagine you're this guy. What do you want to be landing on? What do you want that landing surface to look like? Well, we've got three possibilities. You've got solids, like this piece of rock. You've got, and this is where the particles of the rock are very tightly packed together, and there's very little movement. You have liquids, where the particles are, again, tightly packed together, but they can slip inside with respect to each other. And you have gases. And this is where the particles are very, very small and very, very far apart, and they move basically at will. So these are the three basic states of matter: a solid, a liquid, or a gas. Again, if you're a jumping guy, what do you want to land on? Well, let's look at the important properties of solids. A solid has a fixed shape. So whatever shape it is, it retains that shape. It has a fixed volume. It has minimal expansion when you heat it. It's almost incompressible. So for the purposes of our jumping man, landing on an incompressible surface is going to be bad. It's going to be bad for his body, bad for his bones. Let's look at the important properties of liquids. Liquids have no fixed shape. They assume the shape of whatever their container is. So that's very different from solids. So yeah, if it's a curvy shape, it assumes it. They have a fixed volume, however. So like a solid, it has a fixed volume. It doesn't expand or contract. It has a moderate expansion on heating. Remember, whereas solids only have a minimal expansion on heating. And like solids, liquids are almost incompressible. Some people are surprised by that, but that's one of the important properties of liquids. It's one of the reasons, for example, that people who jump off of bridges don't just have nice, pleasant landings, like plunging into a pool. If you jump off a high enough surface, the water is just as incompressible as concrete when you hit it. So that's why you can commit suicide by jumping off a bridge, which I don't recommend, obviously. So here they're showing as you stack more and more weight, more and more mass on water, it doesn't move at all. It just continues to resist, just like a solid would. So it's virtually incompressible. Here is a video showing the
compressibility of air. The water-filled syringe is compressed until the gauge reads 15 psig. Note that there is no discernible reduction in volume. The air-filled syringe is compressed until the gauge pressure matches that of the previous example, that is 15 psig. Note that in this case, there is a significant reduction in volume.
So just comparing the
compressibility of air. The water-filled
So solids are incompressible, liquids are incompressible, but gases, as we just saw in that last video, are compressible. So let's look at the properties of gases. No fixed shape. So like liquids, they assume the shape of their container. But unlike liquids and solids, gases have no fixed volume. They will fill whatever space you put them in. So you put gas in a room, it fills the shape of the room. You put it in the great outdoors, it just expands and expands and expands. So it has no fixed shape and no fixed volume. It has a massive expansion on heating. Remember, solids had minimal expansion, liquids have some expansion, and gases have a large expansion when you heat them. And most importantly for our purposes, gases are super compressible. So if you're a jumping man, what do you want to land on? Incompressible solid, incompressible liquid, or a super compressible gas? No question. So from a molecular point of view, solids are very tightly packed and very highly ordered. Here, liquid are also highly packed, but they don't have much order. They can slide past each other with very little difficulty. And here, the molecules are very widely spaced apart, and there's very little interaction between them. So, if you're the stuntman, you want it to be gas. And here's how these airbags are inflated with air, which is a gas, and it allows daredevils and jumping men to land safely. Well, let's look at other physical properties. Let's look at color and odor and density and hardness and solubility, melting point, boiling point. These are all characteristics that matter has, and matter in any of these states will have these various characteristics. Let's look at physical changes compared to chemical changes. What is a physical change? A physical change is something like the states of water. So water in its different phases. So you can have water in a frozen state, water in a liquid state, water in a gaseous state. So it's the same thing, but it's in three different states: a solid, a liquid, and gas. But in all three cases, there's no internal change. It's still a molecule of water. It's still good old H2O. When it is a solid, it holds its shape, has a fixed volume. When it's a liquid, it takes the volume of its container, shape of its container. When it's a gas, it takes the shape of its container and the volume of its container. So this is a physical change, and there are lots of physical changes that matter can undergo. So we can describe the change from solid to liquid. So that would be like our ice melting, right? We can go, nice picture. We can go from a liquid to a gas. That would be just like water boiling, going from liquid water to gaseous steam. We can go from gas to a liquid, and that would be condensing. So when water vapor, which is in a gaseous form, condenses on a cooler surface, forms water droplets on the outside of a glass, for example, that's condensation. How about if we go from a solid all the way to a gas and skip the liquid state? That's called sublimation. So here's an example of dry ice, sublimating, going from solid dry ice to a gas. And we can have the reverse of sublimation, where we go from a gas to a solid. This is called reverse sublimation or deposition. And you'll see this sometimes on the outside of a freezer, where again this goes right from a gas to from liquid water right to a solid ice. Finally, we can go from a liquid to a solid. That's good old-fashioned freezing, which happens in some places in winter. So these are examples of physical changes. A physical change is a change in its physical state, but it leaves the underlying substance the same. So here their energy levels are different and their physical appearance is different, but the underlying structure, the molecular structure of water, for example, remains the same. So that's an example of a physical change. Here's another one. Chopping wood, just simply making it in smaller pieces. That is a physical change. But here would be an example of a chemical change. Burning wood. Burning wood doesn't just break it up into smaller parts. Burning wood changes the fundamental composition of the wood, and it reduces it from wood to carbon dioxide and water, and that is a chemical change. So in a chemical change, the atoms are rearranged to form a new substance. They don't just change their state like the states of water, going from ice to liquid to gas, but there's actually a new arrangement of atoms that results in a new substance. And that substance will have a different composition from the original substance. It's often accompanied by observable changes, such as a color change or an energy change. So let's look at some examples of a chemical change. Cooking. So if you fry up some bacon, that is, that's you're making you're denaturing the protein, and you're breaking those bonds, and it changes the chemical composition. Burning things, as we just saw, rusting. These are examples of a chemical change. And one key indicator of a chemical change is that they're harder to reverse. Obviously, you can reverse the state of water. Right? If you make it colder, it goes to ice. If you make it warmer, it melts. And you can convert back and forth depending on the energy. But it's very tough to go from cooked bacon back to uncooked bacon, or from burned wood back to unburned wood, or rusted iron back to unrusted iron. Those chemical changes, they tend to be one way. They tend to be somewhat irreversible. So again, physical change: breaking glass, mixing candy, shredding paper, folding paper, melting ice, chopping wood, cutting hair, sublimating ice, boiling water, breaking an egg. Those are all examples of physical changes. How about chemical changes? Burning wood, rotting fruit, baking a cake, where you take the ingredients and you combine them under heat to make something new and delicious. Rusting metal, using a battery, digestion, milk souring, fireworks exploding, one of my favorites, cooking an egg, photosynthesis. So these are where one or more substances form a whole new substance, not just a change of physical state, but a whole new substance. So the key distinction: during physical changes, forces between particles are disrupted. Things get chopped or separated or moved apart, or in the case of water, the water molecules go from a liquid state where they're touching to a gaseous state. So it's disrupting the forces between various particles. We call those intermolecular forces, the forces between the particles, between one particle and another. So, for example, boiling water pushes one water molecule farther from another water molecule until they finally become gaseous, and then it is bang around in whatever volume. But this doesn't break any of the individual molecules. It doesn't break any of the bonds between the hydrogen and the oxygen that makes up H2O, the water molecule. So these are all still water molecules. They're just further apart than they were when they were in the liquid form. We call this boiling point. When water goes from, something goes from liquid to a gas. And again, it only breaks the intermolecular forces. It doesn't break the intramolecular. That's the bonds between the molecule parts themselves, between one individual. So between the hydrogen and the oxygen in the actual water molecule. So when water boils, hydrogen bonds are between the molecules are broken. They have less attachment to another molecule. But the covalent bonds inside of each water molecule remain intact. To change that, we need a chemical change. So physical changes push the molecules further apart in the case of boiling, but doesn't change the structure of the particles. But consider, so if we just chop this apple up, right, that would be a physical change. We're just separating the pieces of the apple. But in a chemical change, the intramolecular, the forces within the very substance are disrupted. So just again, another example: the inter is the forces between molecules, between this molecule and this other molecule. But the intramolecular would be the forces between the atoms within this molecule, and these are called covalent bonds. And so if those are broken, we have a rearrangement of this molecule into something different. That's a chemical change. So for example, in water electrolysis, one water molecule splits up to form oxygen and hydrogen atoms. And we saw this in class in one of our demos. That's an example of a chemical change. The water is being separated into its individual atomic atoms, and it forms a new substance. We go from water to two kinds of gases. The individual water molecules do break apart in electrolysis, which is a chemical change. And while there's a physical change, if I cut the apple in half, if I leave it out, what happens is that the apple will rot. It will go rotten. It begins begins to oxidize with the oxygen in the air, and it forms a chemical reaction, chemical change. So cutting the apple with a knife is a physical change, but letting it spoil in the air, that's a chemical change. In a chemical change, the reactants, that's what you start with, are converted to products. That's your end result. So here is a very common example. We have sodium plus chloride. Those are the reactants. They chemically combine to give us good old-fashioned table salt. In electrolysis, we start with water, and that's our reactant, and our product is oxygen gas and hydrogen gas. There's always the conservation of mass. In any physical or chemical change, the mass, the overall mass, is conserved. That is, matter is neither created nor destroyed. It's only rearranged, and so this is known as the law of the conservation of mass. Let's look at a heating curve. A heating curve is the way we can explain what happens when things go from these different phase changes. So if we start with solid ice, if we add heat, it will absorb heat up to the melting point. And then if we keep adding heat, it no longer changes its temperature. It doesn't get warmer. It simply changes its phase. So the energy added simply changes it from a solid to a liquid until all the ice is melted. Once it's liquid water, if we continue to add energy, the temperature goes up until it hits the boiling point. And at the boiling point, we continue to add energy, but it doesn't get hotter. It simply changes the phase. It goes from a liquid to a gas until all of it has turned into a gas. Once it's all been gasified, made into a gas, then again, if we keep adding heat, then the energy goes up. So this is a heating curve. Temperature increases until it changes phase, and it doesn't increase until it's all changed into the new phase. Temperature increases until it gets to a new phase change. All the energy added merely changes the phase until it's all changed, and then it continues again. So again, another example of the heating curve of water. If we turn it around, you get the cooling curve. So a cooling curve is simply the heating curve and the same thing. As energy is removed, the gas will decrease in temperature until it hits the condensation point, in which case, as you keep removing energy, it doesn't lose temperature. It simply just is converted into a liquid. Once it's entirely converted into a liquid, you remove energy, temperature decreases until you get to the freezing point. At the freezing point, all the energy added or removed continues to just solidify the solid, and then it will continue to decrease as you remove energy. So the cooling curve is the opposite of the heating curve. Now let's talk about elements, atoms, mixtures, and compounds. An element is a substance that can't be broken down into another substance by chemical means. Each element is composed of only one type of atom. So we've been talking about some atoms. We've been talking about water, for example. It is composed of two types of atoms, an oxygen atom and a couple of hydrogen atoms. Well, each of those is an element. Oxygen is an element. Hydrogen is an element. And every element is composed of only one type of atom. So every element has a different fundamental building block. Here is a periodic table of the elements, and it lists all of the known elements. There's about 100, and it arranges them in a very interesting way, which we'll talk about in later chapters. But the key point here is that every one of these is a different atom. It has a different structure. So all hydrogen atoms are alike, but all hydrogen atoms are different from all helium atoms. All helium atoms are alike, but they're different from lithium atoms, and so on. Compounds are elements bonded together. So we talked about oxygen is an element, hydrogen is an element. When they bond together, they form the compound known as water, a molecule of water. Compounds always have a fixed composition of atoms. So all water molecules, for example, are going to have one oxygen and 2 hydrogen. They contain the same definite amount of each element's atoms. Fashion water, right? 1 oxygen, 2 hydrogen. And that's true of all water molecules. That's the way they're going to be composed. They're not haphazard. So all pure substances, we talk about something that's absolutely pure, they are either elements like oxygen, hydrogen, or they're compounds made of elements. So if we talk about something that's absolutely pure, it's going to be either an element or a compound. Unlike a pure compound or an element, a mixture has varying composition. So we're distinguishing between pure compounds and elements, pure substances, and mixed substances. And mixtures are either homogeneous, that is completely smooth. So we talk about homogeneous milk. That's milk where the cream and the milk have been whipped together to the point that they don't separate. So that's a homogeneous mixture, which is uniform in composition throughout a given sample. Imagine salt dissolved in water. That would give us a uniform composition. It would be a mixture. It's a mixture of water and salt, but because it's dissolved, the composition of the salt to the water is going to be the same throughout. So homogeneous means uniform in composition throughout, but with a composition and properties, that can vary from one sample to another. So I can have 2 different samples of salt. I can have one with twice as much salt in 2 glasses of water, one with twice as much salt as the other. They're both homogeneous, but the composition and properties will vary between the one with less salt and the one with more salt. Oh, yeah. So you can have different salinity, that's the measure of salt, in different bodies of water. Different oceans have slightly different salinity. Different lakes can have different salinity compared to other lakes. The Dead Sea, for example, has a very, very high salt content, whereas the Great Lakes have a very, very low salt content. So mixtures are either homogeneous or they are what is known as heterogeneous. I don't know if you can see here, but this milk has been allowed to separate into the milk and the cream portion there. And so it has not a uniform composition, but a mixed composition. So heterogeneous means it's a mixture with separate, distinct regions that have different compositions and properties. So a classic example is a cookie. Right? This chocolate chip cookie has different areas. Some areas have no chocolate, some are pure chocolate. So this is a mixture of differing compositions. This is a heterogeneous mixture. Cookies. So another quick example, coffee with no cream in it, with nothing floating in it, just pure coffee. Black coffee would be a homogeneous mixture. But a bowl of cereal would be a heterogeneous mixture. Why? Because we can identify the different areas. Here's milky and and smooth, and then here's chunky and flaky. So this is a mixture, but it is a heterogeneous mixture. It's not smooth and uniform. It's chunky and has different areas. So here is a flowchart for helping to classify matter. So matter is anything that has mass, and that matter can be a pure substance or it can be a mixture. If it's a pure substance, then it's either an element, like graphite. The graphite in a pencil is pure graphite, or a compound, such as water, where it is elements combined together to make a compound like H2O. So that matter, if it's a pure substance, it's either an element or a compound. If matter is not a pure substance, then it's a mixture. And as a mixture, it can either be a smooth mixture, like lemonade, or it can be a heterogeneous mixture, like oil and water, that separate out, that have differing areas. And that takes us to the end of our chapter on states of matter. Thank you.